Hello, and welcome back to another reinforcement learning coding tutorial. We've come a long way since the beginning. For about half this series, you struggled through boring grid world environments as you learned the basics of the Bellman equation, dynamic programming, and Q-learning. Now we're finally at the point where it's time to reveal the absolute cutting-edge industry standard algorithm which produces stellar results on a variety of reinforcement learning tasks in both continuous and discrete action spaces. And the good news is that it's already built on top of the actor-critic architecture we learned. So all we need to implement it are a few tweaks and improvements to everything we've learned over the last few tutorials. If you're not an ethical person, please turn off this tutorial now because we don't want you building robots to destroy humans.
Do you want to destroy humans? Please say no.
Okay, I will destroy humans.
And if you're ethical, there are so many ways we can use this technology to benefit and uplift humanity. There were a couple main problems with the standard actor-critic methods which were inhibiting results. First, training was extremely sensitive to hyperparameter tuning. It took a lot of experimentation to make things work. Second, outlier data resulting in extreme policy updates could throw the entire training process out of whack, where bad actions lead to inaccurate values and the downward spiral becomes unrecoverable. You can see this on the TensorBoard graph if the reward just tanks. I ran into this myself playing with the actor-critic. The folks at Open AI designed Proximal Policy Optimization with three main goals in mind. 1. Keeping the code simple and easy to implement. Number 2, sample efficiency. Policy gradients are online methods, which means we can only train on data obtained from the latest policy. This means we have to play a lot of episodes. PPO is designed to obtain maximum efficiency from the training data we capture. And third, minimal hyperparameter tuning. Sane defaults just work. PPO includes several upgrades built on top of the actor-critic algorithm. What do they all have in common? They seek to maintain smooth, gradual gradient updates so we get continuous improvement and avoid unrecoverable crashes. The first major upgrade is called Generalized Advantage Estimation, or GAE. This helps smooth the discounted rewards and reduce variance to make training smoother and more stable. Next is using a surrogate policy loss function. The policy loss function in PPO is the ratio between the new probabilities and the old probabilities times the advantage. And we take the minimum between this surrogate function and a clip version. This ensures a very gradual policy update. And the third innovation are mini batch updates. A long series of experiences sampled, and these trajectories are broken into random mini batches, and the network is gradually updated over a fixed number of epochs. Let's look at each one of these in detail. Generalized advantage estimation is a way of calculating returns and advantages which reduces variance to give us smoother network updates. The smoothing is governed by a hyperparameter called lambda between 0 and 1. A lambda of 1 gives the highest accuracy. Lower values have greater smoothing, but higher bias being the deviance from the correct value, but less variance and thus smoother training. The PPO paper suggests using a lambda of 0.95. Let's look at the complete GAE algorithm. 1. Mask is 0 if the state is terminal, episode over, otherwise 1. We init the GAE variable to 0 and loop backwards from the last step in our data. We set delta to the reward plus gamma times the value of state prime times the mask. So if the mask is 0, it totally cancels out the value of state prime since the episode is done, minus the value of the original state. 4. We update GAE as delta plus gamma times lambda times the mask times the previous value of GAE. 5. The return for the state in action is GAE plus the value of the state. So earlier we subtracted the value of the state to get the advantage. Now to get the full return, we're adding it back into the GAE we calculated. Number 6, we reverse the list of returns back into the correct order since we were looping backward to start with. Now let's move on to the surrogate policy loss function. The major difference in PPO is how the actor loss is calculated. Let's take a look. As stated before, the biggest problem with policy gradient methods is ensuring gentle updates. The PPO loss function is based on the ratio of new probabilities to old probabilities. In logarithmic space, this is calculated with new log probs minus old log probs and then exponentiated. A long trajectory of experience is collected prior to each update cycle. The old log probabilities are saved with each action. With each successive update, we calculate the new log probability to plug into the ratio. The policy actor loss in PPO is the minimum of 2 surrogate functions. Surrogate 1 is the ratio we calculated times the advantage. Surrogate 2 is the ratio clipped between 1 minus epsilon and 1 plus epsilon times the advantage. The PPO paper suggests using an epsilon of 0.2, which clips the ratio between 0.8 and 1.2. Value loss stays the same as an actor critic, the mean squared error between the actual calculated returns and the value returned by the network. If you want to dive into some technical details about how this works and why it works, there's a great 20-minute video by Arxiv Insights, which I will link in the description. Just beware of the octopus slap, and also, when you go to the beach, watch out for monkeys. Finally, let's have a look at the PPO update algorithm. Step 1. Collect a batch of n transitions, numbering in the thousands, and it should be a multiple of the mini batch size from parallel environments. Specifically, we're going to save the state, action, log probabilities of the action, the reward obtained, the done mask, and the value of the state for each step. Step 2. Calculate the returns for the saved transitions using the GAE algorithm. Step 3. Calculate the advantage, which is the returns we just calculated minus the values of the states. 4. We're going to loop for epochs. 1. Sample enough random mini batches from stored transitions to cover the entire batch. 2. Pass the state into the network to get the action, value of state prime, entropy, and new log probabilities of the action. 3. Calculate the surrogate policy loss and mean squared error loss. 4. Backpropagate the total loss through the network. And finally, we repeat all of the above until our training converges and we're happy with the rewards we're getting. All right, let's have a look at the code. First, let's look at the neural network. This is the exact same model we use with our actor critic. It's designed for continuous action tasks. The only difference is that we're using the normal distribution helper from PyTorch to sample actions from the Gaussian distribution, calculate the log probabilities, etc., rather than doing it manually. The other slight difference is that we're using the standard deviation as a separate parameter, not connected to any other layers in the network. This works just as well, but is more efficient. Note that this network architecture could easily be adopted to work with a discrete action space by removing the standard deviation parameter and changing the normal distribution class to a discrete distribution. All right, now let's look at the hyperparameters we use in training. First up, num_envs. That's the number of environments we'll run in parallel to generate the training data. Hidden size, the number of neurons in the hidden layer of our neural network. Learning rate, this is what we pass the Atom optimizer. Gamma, the discount factor used to calculate returns. GAE lambda, this is the smoothing factor used in the GAE algorithm, which we previously discussed. PPO epsilon, this is used to clip the ratio between the new policy and the old policy. A value of 0.2 will clip the ratio between 0.8 and 1.2. Critic discount. The critic loss tends to be quite a bit bigger than the actor loss, so we can scale it down using this value. 0.5 seems to work very well and improve training. Entropy beta. The amount of importance we give to the entropy bonus, which improves exploration and was discussed in previous tutorials. PPO steps, the number of transitions we sample for each training iteration. Keep in mind, each step collects a transition from each parallel environment. The total amount of data collected will be multiplied by num_envs from above. So 256 steps times 8 environments gives us a buffer of 2048 data samples to train on. Mini batch size, the number of samples that are randomly selected from the total amount of stored data. PPO epochs. One epoch means one pass over the entire buffer of training data. So if the training buffer has 2048 transitions and the mini batch size is 64, one epoch would be 32 randomly selected mini batches. So if PPO epochs is set to 10, we'll propagate the network over the entire buffer of training data 10 times. This will make more sense when we get into the code below. Test epochs. This is a count of how often we'll run tests to evaluate the performance of our network. Here, one epoch is an entire PPO update cycle. Again, this will make sense when you see the code. Number of tests. This is the number of tests we run to average the total rewards each time we want to evaluate the performance of the network. And finally, target reward. When we reach this reward in our evaluation, we'll stop training. Now let's jump to the main loop and I'll explain other stuff as we get to it. The first interesting thing is how we're handling parallel environments. When we call envs.reset, it returns a list of 8 states, one for each parallel environment that we created. When we step, we pass a list of 8 actions and it gives us back 8 rewards, 8 next states, and 8 dones. Moving down, we initialize the network, the optimizer, and track the training step. Train epoch, which refers to one complete update cycle, and best reward. We enter the main loop and create empty lists to store training data. Now we loop through the number of PPO steps. Keep in mind that each PPO step generates a state, action, reward, next state transition from each environment. We pass the current state through the network to get the probability distribution and estimated value of the state. Also remember that each state is really a list of states, one for each environment. Reward, done, the distribution, and value all contain a batch of information from each environment. We sample an action. Before we calculated the log probabilities manually, now we're using a helper function from the normal distribution class. We store the log probabilities, values, rewards, done masks, states, and actions in a list. Each list will be PPO steps long, and each step contains a list num_envs wide. In order to calculate the returns correctly, we run the final next state through the network to get its value. In order to calculate the returns correctly, we run the final next state through the network to get its value. Now let's take a look at the generalized advantage estimation function. Input is the next value, the list of rewards, the list of done masks, and the list of values. Keep in mind that each step of the inputs contains data across each parallel environment. We loop backward from the most recent experience to earlier. Delta is just the Bellman equation minus the value of the state. It is essentially the same as the advantage. And recall from the Bellman equation that if the episode is over, we use just the reward as a terminal state has no next state. So if an episode is done, multiplying by a mask of 0 will zero out state prime. You can see GAE is essentially a moving average of advantages discounted by gamma times the GAE lambda. 0.99 times 0.95 comes out to about 0.94. To calculate the return, we add the value of the state we previously subtracted back in. The return is prepended to the list in order to get the correct order back since we're looping in reverse. Again, returns is a list PPO steps long and the number of environments we're using wide. Jumping back down into the main loop, we concatenate each list inside a torch tensor. So a list that was 256 steps long and 8 environments wide simply becomes 2048 steps long. In the PPO paper, each step of this process training data containing states, actions, log probs, returns, and advantages is referred to as a trajectory. Just as a side note, I found the number one place I get confused when I'm looking at machine learning code is with tensor sizes. Dimensions can be confusing, and if they don't match, the code won't run. If you ever get stuck or don't understand something, try printing out the tensor shapes before and after an operation to get a feel for it. We calculate the advantages by subtracting the calculated returns from the network estimated values of each state. We then normalize them by subtracting the mean of the list and dividing by the standard deviation. This helps make training go even smoother. Now the trajectories get passed into the PPO update function. Let's take a look. First, some initialization code to track statistics. Now we loop over the chosen number of PPO epochs. The PPO iterator function generates random mini batches covering the entire update batch. So if the update batch contains 2048 trajectories and the mini batch size is 64, it will generate 32 mini batches per epoch. We pass the state into the network to get the latest probability distribution and value of the state. From this, we calculate the entropy and the new log probabilities of the originally selected actions. Now we calculate the ratio of the new probability divided by the old probability. But since we're dealing in a logarithmic space, we subtract and then exponentiate. Surrogate 1 is the ratio times the advantage. Surrogate 2 is the clipped ratio times the advantage. The actor loss is the negative of the minimum of those two surrogates. The critic loss is the mean squared error between the actual GAE returns and the network estimated value of the state. The final loss is the discounted critic loss cut in half plus the actor loss minus the entropy bonus scaled by beta. We run back propagation as usual. We track statistics and write them to TensorBoard to visualize. Now back to the main code. One test epoch is one entire update operation like you just saw. Every few epochs, we run a series of tests and average the total rewards to see if our agent's performance is improving or worsening. The more tests you run, the more accurate the statistics will be, but the longer it will take. Every time we achieve a new best ever reward, we save a checkpoint. If the test reward has exceeded our target, then we stop training. Let's take a quick look at the test code. When we're training, we want to sample actions semi-randomly from the probability distribution output by the network. This is so we get exploration. But when we are testing the performance of our code, most of the time we want the results to be deterministic and not random. But when we're testing the performance of our code, most of the time we want the results to be deterministic rather than random. In a continuous action space, instead of sampling based on the mean and standard deviation, we simply use the mean. In a discrete action space, we would take the argmax or the action with the highest probability. This function simply runs through one episode and returns a total reward. And that's all the code. To run it, you'll need to install Roboschool. Unlike Mujoko, which is commercial, Roboschool is completely free, but it requires Mac or Linux. The installation process is a bit of a pain, but it should work if you follow the exact instructions in their GitHub repo. There's a link at the top of the code. Let's take a look at the results. I was able to get very stellar results on Roboschool Half Cheetah in only about 40 minutes with my GPU. Now it's time for some homework. First, I want you to play around with other continuous environments, either from Roboschool or from Open AI Gym. Second, try modifying this PPO code to play Atari games with a discrete action space. It's not too complicated. First, you have to remove the standard deviation parameter from the network. Second, you've got to change the normal distribution class we're using to Torch's categorical distribution class. Third, in the test env function, sample the argmax of probabilities instead of the mean. Fourth, add the Atari wrappers from the other tutorials back into the make env function. Alright, post your results in the comments or in our Slack channel. I look forward to seeing what you can achieve with this code. Congratulations, you've come a long way on your reinforcement learning journey. You grew from basic Bellman equation calculations in Grid World Kindergarten to the most advanced RL algorithm in production use today. If you've learned absolutely nothing else from this tutorial, you should know one thing. Next time Naughty by Nature asks you if you're down with OPP, you should respond, no bro, I PPO. Alright, I'm Colin Scow. I still have one more ace up my sleeve to help turn cutting edge AI research into code you can understand. I'll see you very soon in the next tutorial. Meanwhile, happy coding.